Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. Now, in today's video, we're going to be looking now at a topic in which now grade 12 find challenging, right? Which we now refer to it as chemical equilibrium. Okay, so what I'm going to do, I'll try to simplify everything. Okay, I will not just go through this or okay, this is this, this is this. I will be explaining thoroughly. Okay, yes, just that I like this picture. I like this picture because now it gives us a flow in on where to start and where to end, right? Yes. So now, as I've mentioned that our today's topic it is now what chemical equilibrium. Okay, everything that we'll be dealing with with regards to chemical equilibrium. Now, we should be in a position of now understanding what exactly do we refer to when we talk about now chemical equilibrium, right? So when you say something, it is a okay. When we refer to chemical equilibrium, from the word here, equilibrium, we know now equilibrium. It is a state in which now all the forces, if we were to talk physics, the forces are balanced, right? If we now were to talk chemistry, we are now say it is now at a rate where all the things are equal. All the rates, okay, of the reaction are equal. Okay, now let's look at the definition of a dynamic equilibrium, okay, or now chemical equilibrium. So a dynamic equilibrium, it is the rate of the forward, it says now the rate of the forward, rate of forward reaction equals the rate of the reverse reaction, okay? Now this is dynamic equilibrium. Now it means now if you were to be asked to define what is chemical equilibrium, you'll say now it is a reaction in which what the rate of the forward reaction, okay, is equals the rate of the reverse reaction. Do not try to shortcut this and say the rate of both the forward and reverse reaction are equal. No, just write it. The reaction in which the rate of the forward reaction equals okay, the rate of the reverse reaction. Okay, please do not try to shortcut them, the definitions thereof. But now there is another definition here that you can define a dynamic equilibrium with. Now it is what we refer to as amount of reactants and amount of products remains constant. Now, for now, if you're new to this topic, you won't understand why we have two definitions. But now on chemical equilibrium, we have two graphs, okay? The rate graph as well as the I don't know what they call it, the concentration graph, I think. Okay. So now the rate graph tells you, it shows you what happens to now the forward reaction as time goes on. Can you see? Then it will tell you again about the reverse reaction, what happens. Okay. Now, I want you to see something here. Let me. At this point here, can you see? Now, this is what we refer to as equilibrium, the state of equilibrium. Now, if this is the rate graph, this is the point where what the rate of the forward reaction. Can you see? This is the forward reaction, the solid one. Okay. The solid one is the forward reaction. The solid one is the forward reaction. Not always, the examiner will tell you, then now the dotted one, it is the reverse. Okay? Yes. Or however, the examiner will tell you. Okay? Yes. We'll get there as we reach the graphs. I'll explain that thoroughly. For now, I want you to understand where this definition comes from. Okay? And we also talk about the graph of rates, not rates, concentration graph. Okay? Now, this graph tells you what happens to the concentration now of the reactants as now whatever the factors that we'll be discussing affect the equilibrium. Now, we know as in a reaction, reactants are used, right? So it means now the reactant will move from here and maybe here, and now products will move from this point. They will increase. Remember, as in a reaction, as the products, sorry, the reactants decrease, the product increases, right? So now there will be maybe a factor After whatever period of time, then that factor will be fixed. Then they reach equilibrium, uh, like that. Okay. So now in this case, equilibrium, it is the state in which where you'll see all your graph will be like if they are straight like this, like this. Let me do this like that. Like that. Can you see now? It is no longer increasing or decreasing at this portion. So if it is just a straight line like this, like that, it tells you we have reached what? Equilibrium. Now, remember, if this is a concentration graph, it tells you that the amount of reactants and the amount of products remain constant. Okay, so now we are talking in terms of concentration. Now, can you see that the concentration of the reactants is no longer changing? It is constant. Similarly to the what? To the concentration of our products, it is not changing, it is constant thereof. So this is what we refer to by those two definitions thereof. I want to believe you are trying to understand for now. Okay. Now there are requirements that are needed for to consider a reaction at equilibrium, right? So remember, we have many reactions, and not all of them you can consider them as what? As a chemical equilibrium reactions. Now, what do you mean by that? Now, let's look at what it is required now thereof for us to what to be in a position of saying, okay, this is a what? It is chemical equilibrium. All the dynamics of equilibrium are applicable thereof. So now, what we need a reversible reaction. A reversible reaction. If you have been looking at my videos, my previous videos where I recorded energy and heat changing enthalpy, the exothermic and endothermic, there's somewhere where I used this sign here. Okay, where I said, okay, in grade 11 you normally look at this sign like that, but in grade 12 you're going to be now exposed to a new format. Okay, you will be exposed to a new format thereof. Now, which new format do I refer to now? I refer to this format that says the reaction is reversible, meaning this is the forward, this is the reverse. Now, meaning if this is reversible, N2 H2, this is just let me just do this, A2 B2 theoretical, meaning now it is reversible because it can go forward, it can also come in reverse. So this is what we refer to as what? As reversible reaction. Now, a reversible reaction has its definition. Now, what do we mean by a reversible reaction? We say it is a reaction in which, okay, a reversible reaction, it is a reaction in which now products can be converted back to what? To reactants. Very important. Products can be converted back to reactants. Not reactants can be converted back to products. No. Remember the reaction, it is like this. It is going forward. Now the reactants are forming what? The product. But now the products can be converted back to what? To their original what? To their original reactants thereof. This is what we mean by this definition thereof of a reversible reaction. They might ask you, what is a reversible reaction? Do not take these definitions that I'm explaining here for lightly. Okay, everything that I explain here, just take it as it is to the exam room. Okay, you have a level 7 waiting for you thereof. Thank you very much. Now, the first condition we have discussed, it is a reversible reaction, right? Chemical reaction, to be more specific. Then now the second one we need, it is a closed system. Now, what do we mean by the closed system? Now, a closed system, they say now it is a system in which only exchanges energy, not matter, with its surroundings. What do we mean now? They exchange energy. Now let's consider. Remember, I said I won't be saying it is a closed system. It is only exchange energy, not matter, in surround, and move on. Catalyst, like move on. I will explain thoroughly each and every concept that I see here. Okay, I will explain it. Trust me, I will explain it. I'm not that one of a teacher or lecturer or assistant that says now. You see now in today's video, we're going to be looking at the Chatelier's principle. It says this, know your definition, cram it. Now concentrate. No. I will be explaining everything thoroughly, okay? Yes, just bear with me. Just bear with me. Now we are here, a closed system. It is a system that only exchanges energy, not matter, with its surrounding. What do we mean? Let's consider now us having, let's consider ourselves having, let me do an example that is very, 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 very interesting. It is not necessarily a reaction, right? But I want you to see something from this. This is just an example that is not necessarily a reaction. If I'm having a pot here, ne? I don't know how to draw. I know how to teach physics and maths. This is my pot. It looks like a Vaseline. If this is my pot, if I hit this pot, if I hit this, let's say this pot contains water, right? Contains water. This is how I understood what equilibrium, so a closed system. Okay. Now I hit now what this water, that cold water. What will happen there? What will happen is that now this water, the very same pot, will still contain the water, but now the water will do what? The water will be in a position of, the water will be now bubbling inside there, bubbling. Blah, 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 blah. Do you know that sound, right? Yes. The water will be bubbling there. Now what? That water will be converted to what? Do we agree that the same water in liquid, okay? Let me say the same water in liquid form will be converted to what? To H2O, but in a form of what? Of gas. You agree that there is steam that comes out, right? In a form of what? Of gas. But now we know that as time goes on, the very same steam that will be visible on top of I don't know what they call this. Yeah, skyline. I don't know what you refer to in English. Mhm. Yeah, how do we call this? Yeah, whatever that closes the pot, there will be steam in there, right? Steam will rise and reach this point, right? The top of the closer. Yeah, whatever. I'll call it a closer for now. Okay. When it reaches that point, it reaches in a form of what? Of gas. But now, do we all agree that at the end of the day, let me take this. Okay. No. Okay, it's fine. Do you agree with me that at the end of the day, the very same vapor that has risen there to the closet, the thing that closes the pot, that the steam will be converted back into what? Into liquid. How do we know that? How do we know that? We know that because we know if you were to close the um, switch off the stove like this, maybe switch off the stove and maybe water has boiled, it's enough. We know that the very same steam will be now coming back to the original water as in a form of what? In a form of liquid. So this is what we explain when we refer to a closed system. Now, can you agree with me that the very same gas that has risen will go back down at the bottom in a form of what? In a form of H2O, but in liquid form. Do not do this. This is wrong. Okay, this is wrong. What's accepted is you going forward and you coming back. Okay. Yes. Thank you very much. I want to believe that uh, is yeah, is clear. All right. Then you should know an open system. Do you agree with me? If this is open, now, this is our water. Now the steam, what will happen to the steam? The steam will rise, my man. The steam will rise, but can you see now the steam will be going away? So if this is an open system, it means now it is not reversible. Therefore, it means now equilibrium cannot be reached. Okay. Mm. Very, very, very nice. Very nice to pick there off. All right. Now, the factors that affect now our equilibrium now, okay? Remember, we want everything or therefore of ours to be at equilibrium like that. Our concentrations maybe to be at equilibrium. The forward and the reverse reaction are now equal. They are just reversing each other. We are having a back and forth, back and forth. But now there happens times in which now our equilibrium becomes affected. Okay, then we'll be looking at those factors that affect now what that affect our equilibrium. Okay, now when that happen, when that disturbance happen, the disturbance that I'm referring to the factors that affect equilibrium, right? When those disturbances happen there is what we call now Le Chatelier's principle. Now, Le Chatelier's principle, it is a principle in which we use now to do what? To oppose the disturbance. Remember, you wouldn't be happy if you are settling with someone, maybe, let's say, don't know, whatever the case might be there, you are relaxed, like everything is moja, you are at equilibrium, you are fine chilling, but someone comes now and disturbs you, right? Yes. So let's take it as you are on okay, you are just chilling, watching Netflix with your friend at home, just chilling, watching Netflix, and now there is a disturbance. Let's say now there comes a thief. Okay, the thief will do what? The thief will try to do what? The thief will disturb your peace, your equilibrium peace. Right now, what will you do? You will report that to the police station. Now, the police station is what you refer to the Chatelier. What will the what will the police station do? The police station now will come and the police, not the police station, the police will come and do what? And catch the thief. After catching the thief, all the property that was taken forcefully from you, it will be returned to you. Let's say they took your TV, the one that you were watching Netflix with, right? What will happen? The police will say, okay, fine, we're gonna go back, go to those thieves and do what? Take that TV that they stole from you and they will give it back to you. After giving it back to you, what will happen? You will now be at peace again. You will be now in a position of being able to what? To do what? To watch Netflix again. Right? So this is what the concept I want you to understand is now. Le Chatelier is the one that is going to help us do what? Regain the state of what? Of equilibrium. Okay? We will reinstate that equilibrium. Okay? Now, by doing what? By favoring the one, okay? By favoring the one that was stolen from and opposing the one that disturbed us. Okay. Now let's explain this in terms of physical science. I think I've explained in general too much, but general won't be helping you in exam. So now Le Chatelier says to us, it's fine when the equilibrium in a closed system. Okay, Le Chatelier can only help you when you are in a closed system, all right? When it is an open system, when Le Chatelier cannot, okay? It says now, when the equilibrium in a closed system is disturbed, okay? In a closed system, it is disturbed. Remember, a closed system, it is a system in which they interchange water to gas, gas to water. So liquid to gas, gas to liquid, liquid to gas, gas to liquid. Not someone comes now and put a stone or put sand. Now we cannot be at peace. You see, now it says when the equilibrium in a closed system is disturbed, okay, the system will reinstate a new equilibrium. Now we'll try to reform a new equilibrium by doing what? By favoring the reaction that opposes the disturbance. If now the disturbance causes us now, okay, this one, let me explain it like this. Okay, yeah, let me say it is A2 forming B2. Okay. Okay. They are at equilibrium. Everything it is exchange, interchange, exchange, interchange. Let's say now, let's say now, we add heat in here. We add heat in there. Can you see now? The equilibrium is no longer happy. Okay. Why? Because we added heat here. Now, what will happen? Remember, it says uh, in Chatelier'S says when the equilibrium in a closed system is disturbed, this one, the one we initially had, A2 being in a reversible reaction with B2. Now, when it is disturbed, the system will try to reinstate a new equilibrium. It means we will try to reach another equilibrium by doing what? By favoring the reaction that opposes the disturbance. Now, if heat was added in this side, what will Le Chatelier want to do? Le Chatelier will want to transfer the heat on this other side so that what? So that we reduce the heat in here. Okay, remember, there is always heat, right? There is always heat, but we want our heat to be at normal rate. Okay, we want our heat to be at normal rate. So now if we add, okay, let me say we had heat like this. Okay, initially, let me say initially we had heat. So it means now the heat is balanced, is sharp, it does not affect anything. Okay, yes, does not affect anything. Now, what will happen is that if I increase this heat now, can you see now they are no longer at peace because I did what? I disturbed one of the factors here. I disturbed the temperature of the equation or of the reaction. Now, what will happen? The heat in this side, there will be more heat on the right-hand side, all right? There will be more heat on this side, right? But that's not what we want. That's not what we want. But rather, what will happen is that Le Chatelier will say, okay, let's oppose that disturbance now. Which disturbance? Of us adding heat in this side. Let's oppose now the disturbance of adding heat in this side by doing what? By taking this heat and transferring it to the other side. Okay, so that we have a balance in heat, so that I do not only have more heat alone. At least let me share some of my heat with that particular person thereof, so that we are in a balanced state. Okay. So this is what we refer to as now Le Chatelier's principle. Okay. Now we will predict and explain the effect of the factors affecting equilibrium. Okay. Now, the first one I want to start with, it is concentration. Okay. Oh, this one I'll come to it. I'm not ignoring it. I'll come to that one. Okay. I'll come to that one. It has a very interesting stuff, even though it does not have many things, but it is very interesting. Now let's talk about a concentration. Let's say now, uh, oh, okay, here's a reaction that they have given us. Fine. Now let's say there is an increase in that particular concentration. What do they say? Reaction that decrease the concentration is favored. Very nice. Remember, if now the concentration on one other side is increased, the reaction that decreases the concentration is favored. What do you mean by that? Remember, Le Chatelier will do what? Will say now, okay, I won't allow more heat to be on this side. Okay. Rather, I will decrease the heat to the other side. Okay. The other side that we are transferring heat to is the one that we are favoring. Okay. What do I mean by that? Let's look at this one. Let's look at this example reaction here. H2 in gaseous form and sulfur in solid. In a reversible reaction, we form H2S like that. Okay. Now, let's look at this one fact. Okay. This one, now I'll be the one explaining them. I won't be reading them here. I'll just be confirming. Let's say now, okay. We are saying reaction that decreases concentration is favored, right? If there is an increase. But now if there is a decrease, it means the reaction that increases concentration is favored. Okay. Now, let me explain this. Let's start here. Let's say now the concentration, okay, we're going to be using this bracket for concentration of something. Okay. Yes. Now, let's say now the concentration of H2 increases. Now, I want you to check how I do this. I say the concentration of this one. Look at where I put the effect. The effect is what? An increase in concentration. I put it here. Can you see it is going up? There is an increase, right? What will Le Chatelier do? Le Chatelier will say, now, I do not want more heat on this side. On this side. Why are you adding? Oh, sorry. I do not want more concentration on this side. Why are you adding concentration on this side? Why are you doing that? Instead, I will transfer. Look now, I'm no longer doing this one, the thing. I'll be doing this professionally. And Le Chatelier will say, I do not want a more concentration of H2. I'm at equilibrium. We are at equilibrium. Instead, I will do what? I will now transfer the concentration that you added to the other side. This is what we mean. Okay, sharp. I'll come back. This Le Chatelier will say, okay, I'll transfer that concentration you added to the other side. Okay, now this means now we are favoring the what? Can you see now we are favoring the what? This is going there, it is the forward direction. Going there, it is the reverse direction. Can you see now we are favoring the forward direction? The first thing we are favoring the forward. Why? Because the forward is the one that will decrease the what? The concentration. Okay? If we favor this one, I want you to see something. If we favor this one, can you see we will add more concentration to this side, and that's not what we want. We want to decrease it. So instead, we'll transfer it to the other side. Okay? Now, check what happens. When we transfer the concentration to the other side, check what happens. The concentration of this one decreases. The concentration of this one also decreases. It does not only affect when we favor a reaction, like maybe forward reaction, it does not only affect this one, it affects all the side. Okay. Now the concentration of H2 will decrease, the concentration of sulfur will decrease. But now what will happen to the concentration of this one? It will increase. Like that. Like that. So we are favoring the forward reaction, and now number two, what happens? The concentration of H2 and the concentration of S will do what? Will decrease. Whereas now the concentration of H2S, which is our product, do what? Increase. Okay? Instead of saying maybe H2 and this one, you can say the concentration of our reactants, and now say concentration of our products increase. Just like nice and easy like that. Okay? Okay? Remember, the system will try to do what? To decrease the amount of H2 by doing what? By favoring the forward. The reaction that when you reason, you do not say the system will favor the reaction that decreases concentration. You have to tell us that a reaction that was favored. You'll say the system will favor now what? For a forward reaction, or the forward reaction will be favored. Okay, yes. All right, let's look at another fact. I will look at them thoroughly without any rush. Okay, without any rush. Without any rush. Cool. Second one, H2 decreases. Can you see now the forward direction is favored? Okay. Can you see now? We are confirming now forward direction is favored. Now let's look at H2. If H2 decreases, I said put your disturbance here. This is your disturbance. H2 decreases. What will happen? Remember, if this is low, we will try to find a reaction that will add for us. Remember, we do not want this to be low. We do not want this to be high. Now what will happen? We will transfer heat to this side. Remember, at first, we transferred heat to the other side because we already had enough, sufficient in this side. But in this case, we are having short in this side. So what will happen? We will say, okay, you know what? You side, this side, transfer some of your concentration for us because we are running short in here. So this system will say, oh, it's fine. I will transfer some of my what? Some of my concentration to the both of. Remember now, as H2S transfer now concentration to the other side, it does not only transfer to the one who is suffering, maybe H2. No, it will now transfer to the both of them. Okay, what do I mean by that? It means now as H2S transfer its concentration to the other side, which is the reverse reaction now. In this case, can you see now the reverse reaction is the one that is favored? Yes. So it means now what will happen? The concentration of this one will increase. The concentration of this one will increase. But now the question is, what will happen to the concentration of this one? It will decrease. Why? Because there is no way if you are having 60 concentration of 60, then you transfer 10, you'll be left with 60. No, you'll be left with how much? You'll be left with 50. So it means now your concentration will do what? Will decrease. Okay. Now, which reaction did we favor? The one that transferred. Which one is that? It is the reverse reaction. Can you see? Now the reverse reaction is favored. To increase H2. Okay. But it does not only increase H2, it also increases H2 and S. But in this case, S is a solid. So for solid, it does not. Another thing I forgot to mention is that as it is a solid, so concentration won't be affected. Like it won't affect this one. So, but in case it was not maybe sulfur in solid form, okay, or for this one it will remain constant basically. Like I'm sorry, but it's fine for now. Let's just keep it as increase in case it is not solid. Okay, in case it is not solid, it will increase. But if it is solid like this, the concentration will remain the same because it does not get affected. Okay, what will get affected by the concentration is now, let me write it here. What gets affected by the concentration are gases and what? And aqueous solutions. Gases and aqueous solutions. Okay, so now let's not talk about this one basically. It's fine. Let's not talk about this one. Because now why it is not aqueous or gas. Okay, so yes, we're going to be talking about these two. Now, let's look at our last factor. H2S increases. If now H2S increases, let me remove this. Let me remove this. Now, the disturbance. I check what is the disturbance. H2S increases, okay, increases the disturbance. What will happen? You should be asking yourself this. What will happen? Now, we will transfer concentration in this side because there is more. We do not want more. We want less. So how can we decrease this? By doing what? By transferring it to the other side. Then if we transfer to the other side, what will happen to this one? It will try to balance out, but this one will do what? Will increase. Okay, can you see now? The reverse reaction, the one that we are favoring, it is the reverse reaction that is favored to do what? To decrease the concentration of H2S because now it is more. This is that if you're doing life science, you are supposed to get this not necessarily difficult. Why? Because we know in life science we say now, let me talk about what? Glucose. Okay, we know when glucose level is too high, we do what? I can't remember that. The pancreas stimulates the what? Uh, the yeah, I forgot. Yeah, I'm not teaching life science, but yeah, the what the pancreas stimulates the glycogen, then to convert excess glucose to glucagon. Glucagon. Yeah, yeah. I forgot. Yeah, yeah. It stimulates glucagon to do what? To to convert excess glucose to what? To glycogen so that it can be at equilibrium. Okay. So yeah, this is what we mean. We also refer to that like this. Cool. I want to believe the effect of concentration now it is dusted, like it is perfect. Okay. Now with that assumptions, let's move on to what we call the temperature. Okay. I want you to do something a favor for me when it comes to temperature. I'll show you how. Now let's look at sorry. Let's change the highlighter so that we do not become boring. When we look at the temperature, now when you know the temperature either increases or decreases. Now, what happens when a temperature is increased? Endothermic reaction is favored. Why? Why? Remember, we want our system to be at equilibrium with that normal level of heat, with that normal amount of heat, right? Yes, we want it with that amount of heat. Now, if you increase more heat, we will try to make sure that the heat that we are eating, we absorb it because we do not want it. We will do what? We will do what? We will absorb that heat you are trying to add. And remember, which reaction absorbs heat? Remember, we will do what? We will try to absorb excess heat. Excess heat. And if you remember very well, when if you haven't looked at my video there, please watch it. No? It refers to exothermic and endothermic reaction. It is a very basic topic that we inherit from grade 11. Now we say now a reaction that absorbs heat or energy. A reaction that absorbs heat or energy. It is referred to the what? To the endothermic reaction. So hence we are saying now an increase in temperature will favor what? An endothermic. Why? Because we will try to absorb that heat that you are trying to come with and come with excess heat. Can you not see that you are at equilibrium with our normal heat level? Yes. Okay. This is what happens now when you are having fever. All right, you drink the fever medicine. I don't know what they call it. Okay, you drink that fever medicine. That fever medicine does what? That it absorbs your what? Your excess heat and returns it back to what? To normal. Okay. Similarly on this side, if I decrease the temperature now, we are busy here in our heater at 50. When now you come now and decrease our heater to 30, you are disturbing us, right? Now, if you are disturbing us, what we will do? We will try to find a reaction that does what? That releases more heat. People, make this practical. We will find a reaction that increases or that's what that releases heat. Okay, which reaction that we will do? What Rona? What will we do? Try to release more heat because you have come and reduced our heat. We will try to release more heat. So, but now, which reaction, according to the to exothermic and endothermic, which reaction releases heat? Okay, never mind about more or excess for now. We wanted the keyword which is releases heat. Which reaction releases heat? It is now what? Exothermic. Hence now we are saying now, if you come to us or papel and decrease our heat, we will do what? We will favor exothermic because we know exothermic will do what? We will release exothermic will release heat for us. Sham. Exothermic will never disappoint us. Sham. Can you understand that, right? Yes. So this is what we are referring to now. Okay, please try to make this practical so that you do not cram. The reason I'm explaining this in terms of examples and what it is because I want you to understand it. Do not cram it. One thing for sure is that when you cram it now in June, you will forget it. In preliminary exams, it will come. You will cram it again. Oh my goodness. You will forget it after that. You will cram it again on final or in final. Like, how many times do you want to gram one thing? Like, you want to gram one thing 3 times. That's not what you want, right? We want now, we want you to be in a position that after prelims, you are only doing question papers. Okay, no time to cram. You're only doing question papers. Why? Because in grade 12, when you're doing grade 12 now, your syllabus and whatnot ends in term 3, which we call the prelim period. Okay. Now, after writing prelims, you are done. There is no topic that will be added. No topic will be added. It means now we are now doing final preparations. Now you will see now that even your language teachers that teach you Sesotho, Zulu, Sindebele Africans, they will be wanting you more because now they have to prepare you for final. But you are not there. I hope you are understanding the exothermic and endothermic part. All right. Yes. Now let's have an example of a reaction where that reaction we have now. I want you to take this method that I use here. 2 moles of NO2 in gaseous form in a reversible reaction with what? N4, oh sorry, N2O4 in gaseous. Okay, please take note of this. The heat that you are given does not tell you the direction. It does not say, okay, we are favoring this one because it is like this. Every time the heat that you are given here, it is the heat of the forward direction. Okay? This always not, even if they were to give you change in H is greater than 0, it is the heat of the forward direction. This refers to the forward direction. I'm not sponsored by Free State Department either way. I just used their documents because yeah, I feel it is beneficial. So yes, I'm not sponsored. I'm not a teacher at Free State Department. I'm just a student at a university. But yeah, I'm proud to say I come from Free State Department of Education. Like yeah, I studied in Free State, and yeah, there is quality there. All right. So now, the information that you are given with regards to changing age, it always tells you about the forward direction. What do I mean? It tells you that the forward direction here, the forward direction, it is what? It is, remember what does this sign tell us? It is exothermic, okay? So it tells you that the forward direction, it is exothermic. I always did this. Forward direction, it is exothermic, meaning now the reverse direction, it is endothermic. Can you see that? Why am I writing this? So that you will see now the increase means endothermic, decrease exothermic comes from. Okay. Now, another thing that I like to say, I already told you that change in age, it is less than 0. Now, what does change in age less than 0 mean? It means it is exothermic reaction, right? And exothermic, it is a reaction that does what? That releases heat. Meaning, what do they mean? It means now when it releases heat, it means the reaction on this reaction, this one will combust or will do whatever and produce what? This plus what? Plus heat. Because it is a reaction that releases what? That releases heat. So it means now the N2, the product will be N2O4 plus. Always do this on your question, babe. Plus, you can say heat or change in H. Okay, let's write it heat plus heat. Sometimes the examiner won't tell you is less than 0. Maybe the examiner will say change in H is equal to negative 61.3 kilojoules. Just know, okay, it is negative. It means now change in H is less than 0. Okay, please take note of those formats that the examiner might use, that might try to disadvantage you in an exam. Okay, now can you see now we tried to renew our in here button. Ah, so all right, let's try. Let's move on. Now let's say now they say now to us temperature decreases. Okay, what if the temperature decreases? Which reaction will be favored? I want you to see this disturbance. Remember how I always start? I start with the disturbance. Where is my disturbance? On the heat. The temperature is decreased. Remember, temperature, it is in a form of heat. It comes in a form of heat, right? Now the temperature is decreased. Now it means that our heat here, it is decreased. What will happen? We will try to increase our heat. Now we want to regain our heat back. So we'll say what? Hey, this side. We'll say to this side, hey, transfer heat for us on this side. Why? Because we are running low of heat. We are running low of heat. And this one will say, oh, it's fine. I will give you some heat. I will do what? I will give you some heat. I will give you some heat. All right. When that happens, oh, and another thing that I want you to take note of. Oh, no, it's fine. It's fine. In questions, they will say the heat of the system is is uh is uh is decreased. Why? Because now it is in a closed system. So everything that happens in a system. So the products, the reactants, they happen all in a system. Okay. So they will say the heat of the system, the temperature of the system is decreased. But when I just focus on this thing, the temperature is decreased. Okay. Then go to the side that has a temperature, okay, or a heat. Okay. Then now, can you see now? It says, okay, my heat is low. Then what does it say? It says, Le Chatelier says, it's fine. It's fine. I will ask this side. that is not affected to transfer some of their heat to you, okay? Which is what? The forward reaction. Why are we favoring the forward reaction? So as to do what? So as to increase the heat on this side, okay? So as to increase the heat on that side. But what will happen to the heat on this side? We do not care. It will decrease, but can you see now? I don't care. So we just focus on, it will do what? It will increase the heat on the other side, okay? So which reaction is favored? Can you see now the fourth reaction is favored? But I want you to see something. Can you see now the fourth reaction? It is what? It is exothermic. Ha! Nothing. Remember now the disturbance was a decrease in temperature. Now a decrease in temperature favored what? A, a forward direction. But now can you see now the forward direction that you refer to? It is what? It is what? It is exothermic. Now, do you see that it confirms this part here? A decrease in temperature favors what? Exothermic reaction. Okay? Yes. Hence, I say it is important when you get this change in age. What you do first, you say it is the information of the forward direction. So on this forward direction part, you do what? You say, okay, it is exo. Then it means the reverse, it is what? It is endo. Okay? So this is what happens, basically. This is what happens, basically. How nice. How nice. If you follow this technique, trust me, you will never go wrong. You will never go wrong. Ever. Unless I'm not teaching you very well. I'm boring you. Then if that's the case, it's fine. I'm sorry. And I'm sorry. What I'm trying to do here is to help you. If my voice maybe is not that pleasing, I'm sorry. I'm not here for voice code and what. I'm just here to teach you. Okay. Now we saw that the forward reaction was favored. Let's see if it agrees with us. Forward reaction is favored. How interesting of that. How interesting of that. All right. Yes. Now temperature increases. Temperature increases. Good. We come here and say, there's a disturbance in our heat. Temperature increases. Now, what will happen? There is excess heat on this side. There is excess heat on this side. What will Chatelier try to do? Will say, hey, you have more when. You know what? Instead of having more, just transfer one to the other side. Just transfer heat to the other side so that we try to balance our system. Okay. Now, of course, it cannot disagree because it wants to be at equilibrium. Okay. So, okay, after doing that, after now taking heat to the other side, now the heat now will do what? Will decrease. Okay. Now I want you to see. Can you see now the reverse reaction is favored? Yes. But what does the reverse reaction? What is the reverse reaction? The reverse reaction is endo. Is it true? Yes, it's true that when there is an increase in temperature, it favors what? Endothermic. Is it the case here? Yes, endothermic. Why? Because endothermic is the one that is the reverse reaction. No. I explain this, people. If you do not understand this, it means I don't know. It means I'm the problem. You are not the problem. Okay? You are never the problem. It means I'm the problem. I do not know how to explain. But I'm in a position where I feel like I am explaining this so nice. Okay? If not, I'm sorry. If I'm getting ahead of myself, I'm sorry. Now let's move on. Now let's say, let me just do one. Let's change the statement and say we are no longer here. We have moved out there. Let's say now the examiner gives us change in H is greater than 0. What does change in H is greater than 0 mean? Okay, this means now energy is absorbed. Remember, you absorb energy on the reactant, so it means now energy will be absorbed on this side. Okay, will be absorbed. So we will absorb energy so that we form something to break maybe the bonds. Okay. Now, let's say now there is no, I'm no longer looking at this. I'm done with this. Okay, I'm done. I'm now making my own examples. Let's say now there is an increase in remember the information that you're given is that change in H is greater than 0. Okay, so remember I always tell you, I said this is always for the information for the forward. Okay, remember, refers to the forward direction. Okay, it does not mean now when it is less than 0, it refers to the forward reaction. When it is greater than 0, it refers to the reverse. No, they always refer to the forward reaction. Okay, yes. Now, What do I mean? Oh, the fourth reaction, it is endothermic. I write it here. Okay, the fourth reaction, it is endo. And now it means now the reverse reaction, it is what? It is exo. How cool and nice is that? Now let me say there's an increase in temperature. If there is an increase in temperature, it means there will be more heat in this side. Okay? So let's just talk. What does an increase in temperature favor? We know that an increase in temperature favors a reaction that will try to do what? To absorb that. What reaction is that? It is endothermic. Okay, let's see if that's the truth. Now, if heat is increased on this side, what will Chatelier do? Chatelier will say, no, transfer heat to the other side. Stop being selfish. How can you have so much heat alone? Okay, transfer heat to the other side. All right. Now, what if they transfer heat to the other side? What happens to the heat in this side? It comes back to normal. Okay. Yes, it decreases. Okay. Now, I want you to see which reaction did we favor. We favored the forward reaction. But now, can you see now the forward reaction? It is what? It is endothermic. Oh, people, oh, this is nice. I want to believe that you are understanding this. Okay. Now let's have another factor, the last one before we look at our second last factor. Okay, I'm making this video long because I'm explaining this. If I was just a lecture in like 15 minutes to 10 to 15 minutes, this would have been done. So yes, it is because I love you all. I love you all. I want you to pass. Um, okay, I was saying, okay, now let's say the disturbance now, it is now decreasing temperature. Okay, now if there is a decrease in temperature on this side, Le Chatelier will say, okay, do not worry, since well you have less, we'll ask this side to transfer heat for you. Okay, remember Le Chatelier has only one work, only one job, to do what? To try to balance the system. Okay, Le Chatelier has no favoritism. We do not say Le Chatelier does not like this side. While why is Le Chatelier taking it from this side? It's gonna be less. Or no, it's fine. It won't be less. Le Chatelier knows what he or she is doing. I forgot whether Le Chatelier is a male or female. But Le Chatelier is someone's surname. Okay, I think he is. I think he Le Chatelier is a he. I think he is a French scientist, if I remember very well my theory, French scientist. You do not need to know this. They will not ask you in a multiple choice. This is not life science where they ask you who created the structure of DNA. Is it, uh, uh, I've forgotten those names. But yeah, they won't ask you who discovered it, okay? Who died due to cancer? Who took it to X-ray, okay? They won't ask you that, okay? Yes. In life science, they will. You should know your theory very well. So now, can you see now if there's a decrease in temperature in here, we will favor that one, okay? That the reverse reaction, okay? But now, what does the reverse reaction tell us? The reverse reaction is exothermic. Is it true that when there is a decrease in temperature, we favor exothermic? Yes. If there is a decrease, we favor what? Exo. Okay. Yes. So I want to believe now a factor of uh, uh, the temperature effect is now clear. Okay. Mhm. For your information here, take note. Take note. I will emphasize this also when I'm talking about KC calculations. Okay. Only temperature can affect KC value. Okay. Only temperature can affect KC value. I'm not saying only temperature can affect equilibrium. I'm not saying it can affect equilibrium. This one you will understand it when I discuss KC calculations. Okay, let me remove it a bit. But just take note of that. They like to ask it in multiple choice. Now let's go to pressure. Let's go to what? To pressure. Okay. I don't know which highlighter to use. Pressure. It can you see they are telling you it only applicable to what? To gases only. Okay, it is only applicable to gases. It is not applicable to other stuffs. Okay, yes. So now what do we mean? It means now if you are having maybe a solid and maybe aqueous in our reaction, we will not consider that for what I'm going to explain to you right now. Okay? Yes. So now let's see uh, let's see now what this uh, say to us. Okay? Yes. Okay. It says now if there is an increase in the pressure, it will favor or it says the reaction that produces the smallest number of moles of gas. So reaction that produces the smallest number of moles of gas, yes, is favored. Okay. Can you see number of moles of gas is favored? But if there is a decrease, I know when I talk like this, you do not understand. I will make an example so that you understand. If there is a decrease in pressure, you do what? The reaction that produces the greatest number of moles of gas is favored. Okay. Okay. I always took it like this. Let's say you are just and what do you call someone who is shy and who likes to isolate himself or herself, an introvert, right? So yes, let's say now there's an introvert on this side. Okay, introvert. I'll explain it in terms of physics, chemistry for now. For just a moment. For now, let's just take the general. Then in here, we have these are introverts. These are extroverts. Oh my goodness. Wait, I'm teaching English. Fal, HR. Good. Now, I want you to take note of this. Now, now. This person does not like many people, right? Yes. Now, what will happen is that, can you see it says that if there is an increase in pressure, the reaction that produces the smallest number of moles is favored. So, yes, these are introverts, but they only accept, they like it when there are three of them only. Yo, the English is gone. My data of English is dying. Let me quickly wrap this up. Okay, if you're having three people on this side and one person on that other side, now the thing is, we are cool as three friends. I'm cool as one friend. Okay, that is the principle. When you come, when you come and add a person on this side, when you come and add a person on this side, we will say no, 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 no. We are already enough. Take this person and transfer him or her to the side that has fewer people. Now we are already enough. Okay, this is what will happen. The Chatelier will say, okay, no, we only allow three people in here. When I just go to the other side, that person is alone. Okay, yes, this is what Le Chatelier will do. We'll try to take this increase to lesser side. Okay, can you see? It says the reaction, if there is an increase, this is the increase in pressure. The reaction that produces the smallest number of moles of gas is favored. Which reaction is that? The one that leads to fewer a number of people. So now it means now in this case the reverse reaction will be favored. Okay. Now let's say let's say okay, let me just add these two people now. Let me say there are two. It's fine, there are two. Even also the last example I did when I add a person here, it is also applicable. Okay. Now let's say now uh they take away this friend on this side. Can you see they do what? They decrease the number of friends. Okay. They decrease the number of friends. Okay. Le Chatelet will say, oh, no, 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 no. These people, we want them as three, not two. So Le Chatelet will say, okay, I will take one of you here and transfer him or her to the other side. Why? Because now we do not want those to have short people. We like them as three. So I will take you here and you will be transferred. Now you will be now staying on that other side. You'll be like, okay, you are fleeing, you will be now on this other side. Now it is balanced now. Okay? Yes, let's hear this. It says now, when there is a decrease in pressure, the reaction that produces the greatest number of moles of gas is favored. Which one? Which one between the two, if I reverse this? Which one between the two favors produces greatest? It is this one, because can you see there are three? In this one, there are two. So we will favor the one that produces what? The more people, like that. Okay, yes. Now let me talk in terms of chemistry. Hopefully you have a better understanding. Now, let's have our reaction there of 2 moles of NO2 gas in a reversible reaction, N2O4 gas. Okay. Now, we are referring to number of moles. The pressure will affect the number of moles. So first thing first, what you should do, just count the number of moles. Here we have 2 moles. Okay. In this side we have one mole. Okay. Yes. Now let's look at this disturbance. Let's say pressure is increased. Okay. Pressure is increased. So on which side can you increase pressure? On this side. Okay. If pressure is increased, it means now we are affecting this side with more number of moles. Okay. Most people like to like to to struggle with the effect of pressure. Okay. Now, even if you do not do the disturbance, it's fine. You'll say if there is an increase in pressure, if there is an increase in pressure, now we will favor the one that results in less pure number of moles. Which one is that between this one and this one? Do you agree with me? It is that one. So it means now Le Chatelier will say, oh, okay, if there's remember the pressure, it is an increase in pressure of the system. Okay. It is an increase in pressure of the system, not on one side. Okay. But for now, yeah, it's fine. Let me not explain it like that. It's fine. If there is an increase in pressure, now we will go to the side that results or that produces the what? That produces fewer number of moles. Why? Because we are trying to do what? To reduce that pressure. Okay. Yes. Now, if we have an increase, sorry, a decrease in pressure, we will do what? We will favor the site that that does what? That leads to more number of moles. We are trying to increase it, but it means now we will go to the site that has more number of moles. Okay. We will leave the one with less because it is already less. So you will just move to the one that will try to increase the pressure. So hence we say now, if pressure is increased, when P increases, the forward direction is favored. Why? Because now we are trying to go to, if pressure is increased, we are trying to go to the side that produces less. Okay. Remember, Le Chatelier does what? Le Chatelier tries to oppose the disturbance. Okay. Le Chatelier favors the reaction that opposes the disturbance. Okay. If there is an increase in pressure, we'll go to the side that produces few or less. Okay. If there is a decrease, we'll go to the side that opposes less, few, decrease, which is what? Forming more. Okay. Yes. So that is all for pressure. Let's say now you have this. Okay. I want to have these examples. Let's say you have two. You have two. Let me change this. I know it won't balance. It's fine. It is not balanced. It's fine. Let me create mine. Let me create mine. I'll create mine. I should indicate this is gas. So what will happen? What will happen? Now, the first thing that you come, when they talk about pressure, you count. We have 2 moles. Here it was moles again. On this side, how many moles? One from here, one from here. We have 2 moles. Now, the question is, what will happen if the pressure of the system is increased? It means now no one will be favored here. No one will be favored here. There will be just an increase in pressure. So it means it will be just a 50-50, like we are not favoring anyone. You're already equal. So you both increased. We are not favoring anyone. Okay? We are not favoring anyone. Similarly, if there is a decrease in the pressure of the system, this is the Chatelier will say, you are decreasing at an equal rate, Musing. If you decrease, you become one, you become one. Like, why which I do not favor anyone. Okay. Remember, I said Le Chatelier does not have favoritism. Okay. So Le Chatelier will say, oh, I'm not favoring anyone. So it means I will just increase equally like that. It's fine. Yeah. It's your problem. Actually, it's not no one's problem. Okay. So yeah, we are just cool. Okay. Yes. What if you had this? Mm, okay. A plus B, C, and E. Count with me. How many moles do we have on this side? On this side. I'm going to give you 10 seconds to decide. One, two, three, four, five, 10. How many? One mole. Ah, say you are lying. One mole. You are lying. There are two. It is one here and one here. Okay. I hear you. The problem is when we talk of pressure, we only consider gases. Semnomzan. We are only considering what gases. So it means now in this case we have one mole of that A. So it means, oh, say now I hear you. On that other side we have now what? Two moles. Oh, okay. Yes. This one we do not what consider. Okay. Yes. Solid, can you see now solid do not consider it where? On in pressure, we also do not consider it where in concentration. Okay. Yes. So yeah, that's all from pressure. Okay. And pressure has a unique now graph. Oh, before I forget, remember pressure refers to the number of collisions per unit time. Okay. Pressure refers to the number of collisions per unit time. I want you to understand this one because the examiner might not say pressure. Let's say we are having 2 decimeter cubed. This is a volume, okay? Then we are having that pressure. That pressure. Let's say the number of moles or the particles, okay? The number of moles it is 30 moles. Okay. Now, what will happen? There will be what? Collision, right? There will be collision, right? Yes. Actually, let me make an example with a balloon. A balloon is a very nice example. Number of moles it is 30 moles. Okay. Now you know how a balloon is when it arrives from the store. Okay, it is just like this. I'm sure it has no shape. I if you are seeing something, I'm sorry. This is a balloon. Let me write this balloon. Balloon wala jwang? Balloon. Is balloon written like this? Yeah, I maybe. Yo, I say kukupa huetachi. This is balloon because people Joe. Ah, ish, I want a small balloon, man. I don't know how to draw. Hey, let me do it like this. It is a balloon that comes from the store with no shape so that people do not sweat me. Okay? The volume here, the volume here, it is 2 decimeter cubed. When I inflate the same balloon, I'm emphasizing, we're talking about the balloon. The number of moles is still the same. Number of moles is still the same. Now, when you inflate the balloon now, the volume will increase. You agree with me? We all agree that the number of moles in here, they are colliding again. And can you see if there is small space, it means they collide faster and there is frequent collision because now there is small volume, there is small space for them, right? Yes. Now, what happens now if I inflate my balloon? What will happen if I inflate my balloon? What will happen is that I will have my balloon inflated and it will be like blue, like that. Okay, can you see now the same number of moles of particles they will be there, but can you see now they will be now at greater distance from one another? They will be at a greater distance from one another. So now you see what happens. The collisions now becomes less. So it becomes there is no pressure. Can you see when you are in a small room and there are many of you, there is a lot of pressure. But when they release you to the other room where it has a much space, now the pressure is relieved. You can now breathe. Okay. So now the examiner can now say the volume is increased. If the volume is increased, remember the pressure decreases. So it means now this it is volume. The examiner might say the volume increases. Okay. But when the examiner says the volume decreases, when they we decrease now, we go to that room with small space. So now we'll have more pressure. We retlo hemelan. Yes. Now this is what I want you to understand. Okay. Yes. Now I want you to understand that pressure is inversely proportional to what? To to volume. Why? From Boyle's law. Remember what does Boyle's law say? I can't remember. But now from this formula there, PV it is equal to nRT. Okay. Now if I want now, provided that the temperature is constant and the number of moles are constant, did you see that I had 30 on this side? I also had 30 on that side, and temperature was constant. This is also a constant. R is just a constant. Okay. Now pressure, pressure. If I want pressure, I'll say pressure is equal to nRT divided by V. Can you see now? Pressure is directly proportional to what? To T, to temperature. Okay, and what? And number of moles. Okay, this one and this one. Okay, this one is just a constant. Okay, but pressure is what? Is inversely proportional to what? To volume, provided that these at the top are all constant. Okay, then they are inversely proportional. If they are all constant, we take it as one. Okay, so now pressure is inversely proportional to volume. So that is what I want you to understand them. I'm moving to the last part now, which now it is what? Addition of a catalyst. How does the addition of a catalyst affect now our equilibrium? Now a catalyst has no effect on the equilibrium position. What do we mean? It means now, when we say a catalyst has no effect on the equilibrium position, it means now the equilibrium will not shift to the right or to the left. Sometimes, Akiri we said the forward direction is favored. Now, if the forward direction is favored, it means now the equilibrium shifted to the right because the forward is favored. But if the reverse is favored, the equilibrium shifted to the left. Okay. So now it says now a catalyst has no effect on equilibrium position. It only shortens the time it takes to reach equilibrium. Okay. Remember, we try to increase. If we have an increase in concentration or what, we reach equilibrium at a fast rate. Okay, if we increase temperature or concentration, okay, we reach equilibrium faster. But if we decrease it, we reach equilibrium slower. Okay, yes. Okay. The graph of this one will look like this. Okay, it'll be like this is the rate graph. Okay, the rate graph. It'll be like, okay, here we are at equilibrium. If they add a catalyst, what will happen? The forward reaction as well as the reverse reaction. Let me use a different color for the reverse reaction because it's not working out. Okay. If there is an addition of a catalyst, they will both increase at the same time, like that. The rate of both the forward and reverse reaction will increase because the catalyst is not added on the reactants or the product, it's added on the system. So both the products and reactants will do what? Will increase. So it means now the rate of both the forward and reverse reaction will be increased. And now they will reach another equilibrium. And that equilibrium that they reach, it will be equal. Okay, it will be equal. This is what we mean. Okay, yes. Remember, it only shortens the time. Okay, therefore, remember if your time decreases, the rate increases. Why? Remember, in rate of reaction, we said now the rate, it is equal to what? 1 divided by time. Remember, what is the rate of reaction? It is the change in concentration per unit time. So we do not care whether what is this concentration, volume, or whatever. Per what? Per unit time. So it is the reciprocal, okay, or the inverse. Now, why? When we decrease the time, we do what? We increase the rate. This is what we refer to. It shortens the time to reach equilibrium. It means now the rate is at a high. It means now we have a higher rate. Meaning if our equilibrium was here, initial, okay, you're too much, you're too close. Okay, this is equilibrium. Now our equilibrium will be now high. Oh, sorry, our rate will be higher. Okay, our rate. Remember, this is a rate graph. Rate. Okay, our rate was lower. Now they decreased time. They added a catalyst. Our rate will be high. It means we will go up. We will both go up. The rate of the reverse and forward go up. And can you see it is equally? Yes. And then they will do what? They will reach equilibrium again at a higher rate. Can you see now? Can you see? Now, can you see initially the rate was here, but now they added a catalyst. Can you see now where is our rate? Okay. Yes. So that's all for chemical equilibrium, my people. I know when you first saw the video, you're like, oh, so we're gonna be explaining the chemical equilibrium by just looking at this diagram, like what? Like, really? But now, can you see now that the same page, only one page, I explained many concepts thereof. Okay. So thank you very much, folks. Just stay with me and move to the next video where we'll be discussing now graphs, okay, equilibrium graphs. Okay, so yes, thank you very much. If you spot any mistake, maybe in case I said any mistake, please leave out in the comment section so that you help others, those who do not realize the mistake, so that they can be aware. Okay, thank you.